NASA smashed a vending machine-sized spacecraft into an asteroid, and the asteroid's orbit changed more than the spacecraft's momentum should allow. In September 2022, NASA's DART, the Double Asteroid Redirection Test, hit Dimorphos, a moonlet about 160 meters wide orbiting the larger asteroid Didymos in a harmless binary system. DART was about 610 kilograms and arrived at 6.6 kilometers per second, guiding itself into the target from about 11 million kilometers away. It was a planetary defense rehearsal, spot a dangerous rock early, then nudge it off an earthbound path. Add up DART's mass and speed, and you get about 4 million kilogram meters per second of momentum. Spread that over a moonlet weighing a few billion kilograms and you expect a speed change well under a millimeter per second. Yet the orbit shortened by about 32 minutes. So where did the extra shove come from? The answer is ejecta. The impact blasted rock and dust off Dimorphos, and that escaping material carried away extra momentum. Ejecta is the debris excavated from the crater. For a few seconds, the asteroid behaves like a rocket, because throwing mass one way makes you recoil the other way. No fuel burned, no thrust, just flying rubble. Scientists capture that with the beta factor, the asteroid's momentum change divided by DART's incoming momentum. Beta equal to 1 means no help from ejecta. Beta equal to 3 means the debris added 2 extra darts worth of push. For DART, early analyses put beta somewhere around 2 to 4. But can a 610 kilogram impact really launch enough debris fast enough to get beta above 3? Yes, because DART delivered huge energy onto a world with almost no gravity. The impact carried about 13 billion joules, roughly 3 tons of TNT, released where the escape speed is only about 9 centimeters per second. That's slower than a gentle toss, so plenty of debris simply leaves and takes momentum with it. Now, the key trade. With a fixed energy budget, you get more momentum by accelerating more mass at lower speed, because energy rises with speed squared. Slow ejecta is cheap. A small slice of DART's energy, turned into thousands of tons moving a few meters per second, can add extra push comparable to the spacecraft itself, making beta bigger than 1, and the orbit is sensitive. Dimorphos moves around Didymos at only about 18 centimeters per second, so a few millimeters per second is enough to shift a 12-hour period by tens of minutes. Step back, that's why warning time matters. A 1 centimeter per second nudge, 10 years early, becomes about 3,000 kilometers of missed distance. But how did we measure that 32-minute change from so far away? We measured it with a light curve, a record of the system's brightness over time. Didymos and Dimorphos eclipse each other, so the combined sunlight dips in a repeating pattern. Before impact, the dips repeated every 11 hours, 55 minutes. After impact, they repeated every 11 hours, 23 minutes, an orbital clock that had been reset. Space telescopes also saw a debris plume and a dust tail stretching tens of thousands of kilometers, evidence that momentum left in a preferred direction. If that direction is the secret, does the same trick work on every asteroid? No, and that's the uncomfortable part for real planetary defense. The beta factor depends on geology. Some asteroids are solidish rock, others are rubble piles, gravitationally bound heaps of boulders with lots of empty space. Porosity can soak up impact energy by crushing and compacting, leaving less ejecta to escape and pushing beta down toward 1. Spin and impact angle matter too, because they steer the ejecta plume, changing the direction of the nudge. That's why ESA's Hera mission, arriving at Didymos in 2026, is crucial. It will measure Dimorphos' mass, map the crater, and let us tie a number to DART's success. So, what did DART really prove about steering worlds? It proved that a kinetic impact isn't just a punch, it's a way to make an asteroid throw its own mass into space. 1 hit, a spray of debris, a 32-minute orbital change, and when you zoom out in time, that's the whole strategy. You don't need to stop an asteroid, you just need it to miss. A millimeter per second, applied a decade early, becomes hundreds of kilometers of separation. The remaining challenge is prediction. Can we scout a threatening asteroid and estimate its beta factor before we commit to an impact? The orbit changed so much because ejecta carried momentum away, multiplying DART's shove. Like, if this was interesting, hit the subscribe for more and turn that notification bell on.